In this lecture, let's understand some of the registers of the EXTI controller. For that, just open your reference manual and go to Interrupts and Events. And here, go to External Interrupt. So, External Interrupt and Event Controller. If you just browse through this document, you will get this diagram. This one. This is the External Interrupt Event Controller block. You already know that this controller actually produces 23 different lines, and those 23 lines are actually connected to the NVIC of the processor. Out of these 23 lines, 16 lines are used for GPIO pins to deliver interrupt to the processor. If you just observe this controller block, you see there are lots of registers like pending register, interrupt mask register, software interrupt event register, and the rising and falling trigger selection register. These registers you can use to configure the different EXTI lines. That means these lines are controlled by these registers. For example, if you consider interrupt mask register, then this register is used to control interrupt delivery of these lines. By default, this EXTI controller doesn't produce or it doesn't poke the NVIC. It doesn't send any signals to the NVIC unless you unmask the interrupt delivery through this interrupt mask register. And this EXTI controller also has edge detection. Let's say you want the button interrupt at rising edge. That means whenever there is a transition from low to high. How do you think the microcontroller is going to detect that edge, right? So detect that transition. That is done by the edge detection circuitry of the EXTI controller. Here it is, edge detection circuitry. And this circuitry can be configured by using these selection registers. If you want this controller to detect rising edge, then you have to configure a rising trigger selection. Or if you want this edge detection circuitry to detect a falling edge, then you should configure this register. By using these registers, you can configure the edge detection. If you want to understand more on these registers, then you just have to open the same section and go to the EXTI registers here. Here it is. The first one is interrupt mask register. This is used to mask the interrupt. By default, its value is 0. So here you can see that this is actually a 32-bit long register, but only 23 bits are valid. 0 to 22. Why? Because EXTI supports 23 lines. So each bit of this register is going to control one EXTI line. That makes sense. For example, so the first bit controls the EXTI 0 line. By using this register, you mask or unmask interrupt delivery of EXTI lines. By default, this is 0. That means interrupt request from line X is masked. That means by default, EXTI lines, they don't poke the NVIC. They don't send any signal to the NVIC. You have to enable that using interrupt mask register. You have to make this as 1. Interrupt request from line X is not masked. Then only it will send signal to the NVIC. And after that, we are not interested in event mask registers. Let's just forget it. Rising trigger selection register. As I said, this actually controls the edge detection. If you want rising edge to be detected, then you should configure appropriately this register. You have to choose the appropriate value here. For example, if you want a rising edge to be detected on the EXTI 0 line, then you have to make TR0, the 0th bit of this register, as 1, rising trigger enabled. Like that. So similarly, falling trigger selection register. And similarly, software interrupt event register. So the next one is pending register. This is one of the important register of the EXTI controllers. You are going to use it in this course whenever you code for the EXTI block in future lectures. Basically, this register updates the event which takes place on the EXTI lines. This bit is set when the selected edge event arrives on the external interrupt line. Remember that this bit is cleared by programming it to 1. So you know that PA0 delivers its interrupt to the processor over EXTI 0 line. Now let's say the EXTI controller is configured for rising edge detection on this pin. And let's say you press a button and you make a low to high transition on this button, so which is a rising edge, isn't it? Whenever the rising edge happens on the button, the EXTI controller detects it. Okay, when that detection is successful, the corresponding bit in the pending register goes high, indicating the selected edge event has occurred on the EXTI line. When the selected edge event happens, the EXTI control makes this EXTI 0 line as 1. Now, let's assume that these two lines are connected to a simple OR gate here. And when both the inputs are 1 and 1, the output will be 1. That output is actually connected to the NVIC. So NVIC gets the signal, isn't it? So when NVIC gets the signal, interrupt is triggered, right? CPU runs your interrupt service routine. So now when this signal goes away, EXTI controller deasserts this EXTI 0 line. It makes it 0. You can see that still this OR gate produces 1, isn't it? Because the pending register is still holding 1 here. It is indicating the past event. Basically, the EXTI controller doesn't clear this bit. This bit is not cleared automatically. The programmer should clear it. And how to clear this bit is also mentioned in the reference manual. You can see that this bit is cleared by programming it to 1. Suppose if this bit is set, then you have to write 1 to it to clear it. Okay, not 0, remember. That's a design. To clear this bit, you have to write 1. So once the ISR handler runs, you do whatever you want to do in the ISR handler and then clear this bit. So what happens if you don't clear this bit? So if you don't clear this bit, you can see that this OR gate produces always 1, isn't it? So that means this line will be high always. So that means the processor will get continuous infinite interrupt. So once you exit the ISR, again interrupt happens and there will be spurious interrupts. So that's why you should clear this bit once it is set. Now let me demonstrate this with small example of button interrupt. So here I have a project. So you are not expected to understand any code here because we have not yet explored the GPIO controllers and other programming things. Those things will be covered later. Just for the demonstration purpose, I'm going to show you a couple of things. This program is coded to receive the button interrupt. So you can see that there is a interrupt handler written. Look at the name of this interrupt handler, EXTI 0 IRQ handler. Why? Because the button which is there on the STM32 discovery board issues interrupt on PA0, right? So PA0 interrupt comes over EXTI 0 line. So that's why I have to write EXTI 0 IRQ handler. If you are wondering how did I get this name, it's very simple. You can go to your startup file here and you can browse through this and you get the name here. For example, here it is, EXTI 0 IRQ handler. You actually see a dummy implementation of this EXTI IRQ handler here. This is a dummy implementation which is attributed as weak. So I'm just overriding this dummy implementation of this ISR in my code. So whenever the button interrupt happens, the control will come to this point. So I'm going to keep a breakpoint here, and I'm going to the debug mode here, and I'm going to hit run. Code is running. If I suspend this execution, you can see that the code is in the while loop. Code is running now. I'm going to press the button on my board, and you can see that the interrupt is triggered and the processor jumped to my IRQ handler, isn't it? Here, let's examine this register, EXTIPR. How do you get the address of this register? So you have to add this offset to the base address of the EXTI peripheral, isn't it? You have to add this offset to the base address of the EXTI controller register. For that, let's go to the memory map. In the memory map, you can see that so EXTI controller is hanging to the bus APB2. You can see that EXTI controller is connected to the APB2 bus. This is the base address of EXTI registers. This is a base address. Okay, let's check this register. Okay, I'm going to copy this and let's go to the memory browser and let's paste here, and for that let's add this offset because we are going to check this pending register +0 cross 14. Right, here it is. Now you see here the 0th bit is set because the selected event has happened on that line. Once the selected event has happened, the interrupt triggers. As you can see here, we are in the interrupt handler, and I'm going to do some work here. And before leaving the interrupt handler, you have to clear this bit by writing 1 to this position. This is actually the address of the pending register. Okay, so which you can. Once I do that, I'm going to do a step over. Right, here it is. This code has cleared that bit. So now everything is normal. Okay, the interrupt has exited and there are no more interrupts. If you don't clear this bit, then as I said, there will be continuous interrupts will be delivered to the NVIC, and the processor will keep on triggering this ISR execution. So I hope you got a little idea about how the GPIOs deliver their interrupt to the processor. Okay, in between there is a EXTI controller, and all these points are required later in this course when you write your own GPIO interrupt APIs. With that note, I would like to end this discussion on interrupts, and we'll surely see some more points when we code for our driver APIs. Let me know if you have any questions, and I'll see you in the next lecture.